So in the previous video, we have calculated the entropy change of an ideal gas system in terms of the uh, volume and temperature. Now here we will try to derive the entropy change in terms of the pressure and temperature. So the logic remains the same. Will be depending on the equation for infinitesimal change of entropy. ds is equal to d bar q r upon t, and we will be substituting for d bar q r upon t by using the differential form of first law of thermodynamics in terms of proper quantities. Okay, so let's begin in the same manner. So we have the differential form of first law of thermodynamics. What is that? We are writing in terms of q. So d bar q r is equal to, for the reversible process, is equal to du plus pdv. So let's start from here. Let me say this is my equation number 1. Okay, so and we can rewrite this equation in terms of the Cp, in terms of the heat capacity at a constant pressure. Equation 1 can be rewritten as, so I'm avoiding those steps. Already we have done it in the discussion of Mayer's relationship, or in proving PV raised to gamma equal to constant. You can refer back, or you can just try to do that by yourself now. So in terms of that one, I'm rewriting this d bar q r. So when you write, you'll remember right thing. So it is Cp dt minus VdP. For an ideal gas system, we'll be able to get it like this. So that is my second equation. Okay, so hope you remember the corresponding equation that we are used in the previous derivation was d bar q r is equal to Cv dt plus pdv. These two are very similar equation. Here it is Cp dt minus Vdp, and the other case it is what, Cv dt plus pdv. Okay, so please refer back to those equations in order to save time. I'm just skipping that thing. Remember, it is for ideal gas system, so PV equal to nRT is always applicable. And also PV equal to, that will be using every time nRT for n moles of the ideal gas. So let me call that on as equation number 3 for the time being. Okay, and now let's come to our target equation. See, for a reversible process, right? So also ds is equal to, this is the equation that will be just using in all these derivations. D bar q r is our motivation. Okay, target equation by t. So let me call this one as equation number 4, and our aim is to integrate equation number 4 by properly substituting for the d bar q r from the previous equation 2. Okay, so we can substitute for d bar q r from equation number 2. So what will be that one? So it's equal to d bar q r. So that is Cp dt by t, minus Vdp, splitting it into two terms, Vdp by t. Okay, so that is the right side. Actually, I am multiplying equation number 2 with the integrating factor 1 by t. Okay, and then rearranging that one. That's what we are doing. Our purpose of integration, right? So ds is equal to. Now let's modify this one. Let's look at this equation whether it is a readily integrable terms. So left side it is ds. Okay, exactly differentiable. We can differentiate it. On the right side also, Cp is a constant, can be treated as a constant for ordinary temperatures. Cp into dt by t, of course, that is also a readily integrable thing, but Vdp by t. Okay, so Vdp by t, that's not seemingly fair. Okay, V is varying, P is varying, as well as T is also varying. okay, because all P, V, T are undergoing variation in our thermodynamic process in general, okay. So I should do something with the second term over here. So what can be done? You can see that here you have got in the second term V by T. So from equation number 3, can't you get something from V by T? So what will be V by T from this equation? That is V by T, can't you substitute it as what? V by T. So it will be equal to simply NR by P. NR by P. And is it not beneficial? Okay, so this equation will give you these equations. Yeah, it's beneficial. Why? Because here N, R both are constants and only P is the variable. And here we have got dP here. So it's all fine. And not only that, you know, our aim of this particular derivation is to express delta S in terms of P and T. Means we should somehow get rid of the volume V from these expressions depending on our aim. And that is what we are actually doing. Okay. So I'm substituting this one. So this is equal to, further it's equal to, or I can write it here itself. It's equal to Cp into, I do not touch the first term at all because that is, okay, no, a part of our equation what we need. It is readily integrable. So dt by T minus, okay, I can write this one as some NR, okay, NR times dP over P. So I'm just writing it in a form. So that is there. Now you know what to do. It's simply a matter of okay, integration directly. Okay, so integrating. Okay, so ds I will be integrating, integral ds. You know from where to where? From the initial value s1 to some final value s2. Okay, on the right side I'll be writing Cp. Cp is treated as a constant throughout the process for the range of temperatures involved. So it will be T1 to T2. I should integrate it with respect to the variable temperature, dt over T. You can skip many of these steps, it's all up to you. Minus NR, both are constant, integrating from, pressure is the variable here, dP is there, so I'll be writing from P1 to P2. Okay, dP over P. And you know what will be the result of this equation? That's going to be, okay, yes, I'll be write it here. So finally, that is, yes, that's equal to S2 minus S1. Won't it be? You can directly do that one. S2 minus S1, that's equal to, okay, so it will give you Cp, you know, capital Cp. Then this one should give you log T from T2 to T1. So I can write directly that one, log of T2 by T1, right? Log of T2 by T1. We have done it in the previous derivation also. It was instead of Cp it was Cb. That's only difference. Then there is a minus sign here. Be careful about that minus sign. That's the difference. Minus NR log its pressure here, so it will be P2 by P1. That's all. P2 by P1. Now it's up to you to modify in different forms. Okay, so this equation, okay, this equation can be taken as a final expression that is of use to us, right? S2 minus S1 is equal to Cp log T2 by T1 minus NR log P2 by P1. It will look very similar to the previous expression. Only the change here is that in place of okay, what is that, volume, the pressure is there. So here in the previous expression it was Cv log, okay, T2 by T1 plus NR log V2 by V1. So here there is two notable differences. Instead of Cv, Cp has come in, and instead of plus NR, there is what? Minus NR here. So maybe finally you can tabulate all the expressions and compare it and try to recall it as per the dependence. Okay. What I suggest is that we can even derive it shortly if you know the method what you're doing. Okay, it can be done within some 1 or 2 minutes. I'm just explaining it in detail. Okay, fine. So that's expression. Now in what all ways, other ways you can express it? Of course you have got the freedom to write it in some other way also. What you can do is that here whenever you find NR in the expression, see that you always remember by NR is equal to actually Cp minus Cv, because this is a capital Cp and capital Cv, the heat capacities, not specific capacities. Okay, so you can write it in that way, or you can write see this in terms of the molar heat capacities. You can write small Cp and all, you can write that also. So if you are writing small Cp, then you know small Cp is equal to capital Cp divided by N. So when you are replacing this capital Cp, you can write this one even as what? Small n into okay, no, small cp, right? N into small cp. It's all up to you. Then everything else same, a log of t2 by t1, okay, minus small n r into log of p2 by p1, depending on your requirement. See that you modified. So this is also a modifiable equation, or in place of nr you can substitute a cp minus cv. Okay, so that's about the entropy change derived in terms of the pressure and temperature for an ideal gas. Okay, fine. Now in the same manner we are left with one more attempt. What is that? That is for in terms of you can say the volume and the pressure, right? So we have seen the combinations of temperature, volume, then temperature, pressure, then what is left out is pressure and volume, or volume and pressure. So let's do that one also. Okay, so we'll do in the next slide. Same manner, it's only a matter of, okay, the strategy should be well and clear. Okay, we are always using ds is equal to d bar q r by t, and we are substituting for d bar q r from the first law of thermodynamics in proper form. Okay, and eliminate either p or v or t to reach an integrable equation. That's all. Okay, so let's start in the same manner. So you know the starting point by the time. So we have from the first law, from first law, what is that equation? D bar q r. So only to have a beginning, let's write the formal form. D bar q r is equal to du plus p dv, du plus p dv. Be very careful because my u and v are looking very similar. Listen to my audio also carefully, otherwise also you can understand that. So that is my equation number 1. Can you rewrite that in terms of cv once again? So in terms of cv, okay, d bar q r can straight away begin, but I'm just writing it for the sake of, okay, your value points and all in exams, okay, which I cannot neglect for the time being. So it can be written as, how do you write this one? That is, this is the first derivation we have done, cv dt plus p dv. So straight away can begin from here. This is also first law of thermodynamics. So let me call it for the equation number 2. Now, okay, so we have got also for, let me bring in all the necessary equations for ideal gas. What is the other thing that we have? PV equal to nRT, which can be of use any time. So that also I am bringing in. Okay, I am arranging all the equation that is of that will be of use for me, and entropy change, right? Entropy change. What is the equation of our dependence? So entropy change ds, infinitesimal change in entropy ds, is equal to d bar q r upon t. Remember, in all these cases we are considering reversible process. Okay, that because that is the easiest one to deal with. Okay, ideal one. So that is my equation number 4. Now you know what to do. Okay, you have to just modify that. Okay, so can you substitute equation number 2 in equation number 4? So I am writing it from here. Therefore I can write ds is equal to equation number 4. I am modifying ds is equal to 1 by t. So it will be cv dt, capital CV dt upon t. So that is a readily integrable form, so I need not modify much about that. Plus I can write it's, what is that, p dv by t. So it's a p dv by t, okay. So my aim is to get it in terms of p and v. Okay, here there is temperature, here I will be using it, here p. Let me do one more modification here, so which is further equal to cv. You will understand why it is done this way. You can do it in several other ways also. Some motivation is there with me. So dt by t, okay, plus that p by t for the time being. Okay, p by t in this here, let me substitute it by using, what is p by t equal to nr by v. Can you substitute as nr by v? So I am writing this one as nr by v. Okay, nr by v dv. Okay, so that is what I am doing. So let me say that this is my equation number 5 for the time being. So just modified. Now let's see how it will be of use to us. Now let me use equation number 3. So taking differentials taking differentials of equation 3 on both sides. What do we think? Remember, all that P, V and T, all the three are variables here. Okay, that is in general. We assume that pressure, volume, temperature, all are undergoing change. In a special case of isobaric or isochoric, maybe one of these is not, but we are doing the general derivation. So what do we think? So P UV form. So it will be what? P dV plus V dP is equal to nR dt. That will be the thing. Okay. So let's do one thing. Let's divide throughout by nRT. We are dividing throughout by nRT. So dividing by nRT throughout. What do you think you will be getting? So it will be P dV by nRT. So it's simply a mathematical technique, plus V dP by nRT is equal to, on the right side you will be getting dt by, because nR will be getting cancelled, so it will be dt by T only will be remaining. Okay, dt by T only will be remaining. So now instead of this nRT, can you write directly PV? So here you are substituting PV. So when you substitute PV in the denominator of left side, okay, two terms on the left side, what will happen is that this further becomes P and P will be getting cancelled, so it will become dV by, is not dV by V, because this nRT is equal to PV. Okay, so P and P will be getting cancelled. What remains there is V, dV by V plus what? Here what happens? PV comes, V and V will get cancelled. So it will be what? dP by P. Can you see something? Okay, beautiful. So dV by V plus dP by P is equal to dt by T. That is also a mathematical relationship holding good for ideal gas systems. Okay, differential changes in volume, pressure and temperature are always related by this equation. So let me say that this is my equation number 6. You can even remember this equation as a standard result for ideal gas. Okay, so now let me substitute this equation number 6 in equation number 5. So we will substitute this equation number 6 in equation number 5. Let me do one thing. Let me complete it. Try to complete it here itself. That'll be fine. Okay. Yeah. Here it is. So equation 5 becomes, what is the fate of equation number 5? That's what we are going to see. What is equation number 5 becoming? That is ds is equal to, once again, ds is equal to Cv dt by T is there, right? Cv dt by T is there. So you can substitute for dt by T. Okay, dt by T. So it will be Cv into, I can open bracket. So from 6 you are substituting for dt by T. So what is dt by T equal to? dV by V, dV by V plus what? dP by P. It's simply a mathematical manipulation, nothing else is there, no other physical thing involved. Plus what? Plus nR, the same term here, whatever. Okay, plus nR dV by V. I am writing in an integrable form, dV by V. And can you see here straightforward that there are two terms containing what? dV by V. Okay, so you can just write that one as what you can do. It is Cv plus nR times dV by V plus Cv into dP by P, opening the bracket and rearranging. And what is Cv plus nR? That is Cp. Okay, so it's further equal to Cp into dV by V plus Cv into dP by P ds. So that is a major intermediate equation. So let me give some number for that. Let me call it some equation number 7. Now it's straightforward. Okay, why? Because our aim is to get equation in terms of P and V. Here you can see that V comes here, P comes here, nothing else is there. So now it's a readily integrable form and you can obtain that. So integrating on both sides within the proper limits and all, I'm just straightforward writing. You can, you know, how, where we will be ending. So integrating over proper limits, integrating, what will be getting? You'll be getting S2 minus S1, or it's equal to delta S. Okay, that will be equal to, what is this equation? Cp log V2 by V1, Cp log V2 by V1 plus what? Cv log P2 by P1, and that is our final expression. That's our final expression, which can be modified in several ways. What you have done. Okay. So you can write in terms of molar specific heat in the way in which we have done with the previous case. So let me summarize it. Sorry. So let me summarize all the three equations that we have derived. Okay, so I'm writing it as S2 minus S1. For the time being, I'm writing it as delta S. So delta S is equal to, these are the equations that we have derived. Delta S is equal to, first one what you derived was Cv log T2 by T1 plus, I'm writing only one equation, other one equivalent ones you can derive, plus Nr log V2 by V1. Okay, one thing. That was in terms of T and V. Then the second equation that we have derived is delta S is equal to, just see the changes, Cp log T2 by T1 minus, there was a minus because of the change in our starting equation. Okay, so always remember, try to remember this equation in terms of the derivation. That's why we are doing derivation in detail. Minus Nr log P2 by P1. And the third equation which we have derived right now, that is delta S equal to Cp log, right, V2 by V1, okay, plus Cv log P2 by P1. So these are the sets of equations that we have derived. All these equations are giving you the change in entropy of an ideal gas in terms of the three thermodynamic variables. Okay, so I just conclude the session here by telling you that these equations, any of these equations which we have to select, can be now used to find out the entropy change of an ideal gas in various specific thermodynamic processes. What are the specific thermodynamic processes? For example, isothermal process. So some T1 will be equal to T2. Okay, so you'll be getting rid of one term out of this equation. Or for isobaric process, so in that case P1 will be equal to P2, so one term will be getting cancelled out in from that proper equation. Or for isochoric, similarly one term will be getting cancelled out. And also for adiabatic, that is a very special case. Hope you remember the entropy change during an reversible adiabatic process is always equal to 0, and hence we have concluded that an reversible adiabatic process is always an example of an isentropic process. Okay, so we'll do that those calculations in the next session. Hope it is okay. Thank you.